Hello everyone. In this video, we are going to discuss about the amount of work done, or we can also say energy expended in moving a point charge in the presence of an electric field. Before starting with that, we will understand with the concept of moving an object under the force of gravity. We all know an object which is present in the force of gravity can be moved by exerting equal and opposite force of this gravity from one point to another point. We can take this analogy to this charged particle, where this charged particle is already present in the force of an electric field E. Here, this force of gravity can be taken as analogy to this force of electric field which is already existing in this region. Now, if I try to move this object from point A to point B, I'll be giving a force which is equal and opposite to this force of gravity, and then this can be moved through a displacement dl. In a similar way, if I consider this charged particle Q has to be moved from one point to another point against the force which is exerted by this electric field E. So we can define work done as force through the displacement. We know force is a vector and displacement is also a vector, but the work done is a scalar quantity. We can multiply these two as a dot product mathematically. Now this is through a small distance dl, thereby a small amount of work done in moving the charge q through a small displacement dl can be given as force multiplied with dl. If I find the total work done, then this can be estimated by doing integration of this f dot dl with the limits as the initial point being the lower limit and the final point being the upper limit. So we can now estimate how much of force is required to move this charged particle Q from point A to point B. So already this charged particle Q is under the force of electric field that is given by force which is Q into E. The amount of work done requires equal and opposite force to this existing force in moving the charge from point A to point B. So the force applied to move the charged particle will be negative of this QE. Now this applied force decides this amount of work done. Thereby, this differential amount of work done can be given as minus Q into E dot dl. And we can estimate the net work done from point A to point B as integration of this quantity, with the lower limit being the initial position and the upper limit being the upper position. We can now understand the significance of this line integral. Before that, I would like to tell the work done is a scalar quantity where force through the displacement can be estimated in the units of joules. So joules is the unit of work done, and this minus Q integration of E dot dl with initial position as the lower limit and final position of the upper limit gives the estimate of amount of work done. Now let us understand the significance of this line integration. So we can consider a straight line segment from point A to point B, or we can take any curved paths or any random paths in moving the charge from point A to point B. Let us try to understand how this different paths is going to influence the amount of work done in moving the charged particle, being the initial and final positions same. So let us consider this path 1, and this path 1 is a curved path where this path 1 can be separated into 5 line segments which are straight. So I have considered here DL1, DL2, DL3, DL4 and DL5 are the 5 straight line segments comprising this path 1. Now, if I estimate the total amount of work done in moving the charged particle from point A to point B through this path, I can consider a small amount of work done in moving through a length DL1 plus a small amount of work done in moving through the length DL2 plus a small amount of work done in moving through the length DL3 plus a small amount of work done in moving through the length DL4 plus a small amount of work done in moving through the length DL5. That comprises the total amount of work done from point A to point B along this path 1. So we can write the differential work done through this path 1 as summation of work done through this 5 line segments, where each line segment length is DL1, Thereby, we can write the work done for each line segment is minus q E dot dl1, then minus q E dot dl2, minus q E dot dl3. Likewise, we can write the small amount of work done for all these 5 short line segments along the path 1. Now we know the charge Q is same and the region having the electric field intensity is same. So we can take this QE as common term from all these 5 terms in the summation. Thereby, we can write minus QE dot DL1 plus DL2 plus DL3 plus DL4 plus DL5. Now, when we consider the vector addition concept, if I have, suppose here, let us take the example of adding these 4 vectors A, B, C and D. The addition of A plus B plus C plus D will give the resultant vector A plus B plus C plus D from A to D. So this straight line joining A to D gives the net addition of these 4 vectors A plus B plus C plus D. This is by the concept of general addition of vectors. In a similar way, if we consider the addition of DL1, DL2, DL3, DL4 and DL5, this all 5 line segments addition will result in the straight line displacement from A to B, which is nothing but DL. So I can replace this 4 vector summations DL1, DL2, DL3, DL4 and DL5 as DL simply, and thereby we get the differential amount of work done is minus Q E dot DL. We get the net work done by performing integration over this entire length with the initial position as the lower limit and final position as the upper limit. And also, if we consider the movement of charge around this path 2 also, if I consider many line segments along this path 2, all their summations will add up to this same displacement dl. Thereby, we can conclude work done is same irrespective of the path chosen. So that is the important significance of this line integration in estimating the amount of work done, where work done remains same irrespective of the path chosen, because here we are considering the displacement from point A to point B. And one more thing, if I consider moving the charge around a closed path, means if the initial and final position is same, then the initial and final limits are same, which is going to give the answer of integration to be 0. We can conclude if I take the charge around a closed path, then the total work done around this closed path is 0. Also, we can say if I take the charge around a closed path, which does not mean no work is done, which means the work is done where amount of energy spent and amount of energy gained, the net value is 0. Means equal amount of energy is spent and equal amount of energy is gained by the system, which is trying to move the charge around a closed path. That indicates work done around a closed path is 0. And one more important thing which we have to consider is, in general, when we consider this work done with the electric field intensity E, if this work done is same irrespective of the path chosen, then this electric field intensity is conservative in nature, and thereby we call this E field as conservative electric field. So these are the realizations of the line integration in evaluating the work done. And we also have understood work done around a closed path is 0, which indicates the amount of work done is 0, which says the energy spent is again gained by the system. That indicates the net work done is 0. Thank you for watching the video.